Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing our discussion for chemical process design using the textbook by Turton et al., looking at reactor performance and design particularly. And so that's what we will spend the next few video lessons looking at. Now, reactor performance is going to really be very closely tied to four primary issues that we need to look at. And the first of these that you start studying back in your mass and energy balance class is just how much of the desired product will you create. And so this is done through calculations of conversion or selectivity or yield for multiple reactions. And those are very important and are going to be closely tied to how well the reactor can perform. Part of this is going to be determined by the reaction kinetics. This is how quickly the reaction can happen in the specified configuration of your reactor. This will vary with concentration of the materials, temperature, pressure. What exactly is the reaction mechanism? Is there a catalyst present? And then are there thermodynamic limitations such as equilibrium? The reactor itself plays a great role. So part of it is about what type of model are you doing? What's the volume or the space-time of this? How long is the material present in the reactor? Are you using a catalyst, and how is it going to interact with the chemical, the feed material? And what's the reactor configuration? And then we have heat transfer concerns. Reactions are always either exothermic or endothermic, and those each have their own special concerns with how to operate them. Exothermic reactions have some specific safety issues that you can develop hotspots and eventually sometimes runaway reactions. And we, of course, want to avoid those possibilities. And so the configuration of our heat exchange system is going to be very critical to the performance. We want to look at kind of how we model our reactors in our simulators, and we're going to have to provide a lot of information. And the first of these is the reaction stoichiometry. Remember that you use negative coefficients on reactants and positive coefficients for your products. And then you're going to need to have procedures for calculating the conversion, the extent of reaction, what is the equilibrium, and the kinetics. And we'll look at the first couple of these in this lesson. So conversion reactions rarely go to completion, and so therefore we define the fractional conversion is the ratio of the moles of A that react compared to the moles of A that were fed. And so here for this simple problem taken out of a mass and energy balance class, we have calculated the fractional conversion. Notice that if your feed is not stoichiometric, then the fractional conversion of every element fed will be a different value. If you have multiple reactions, you need a little bit of additional terminology or ratios that you're going to need to define. Single pass conversion is how much happens within the reactor just the very first time the material passes through there. If you have a low single pass conversion, you're going to need to have a large recycle stream, which affects costs, but it also, it's not the end of the world if you have a low single pass conversion. The overall conversion is going to be looking at the total system based on how much reactant is fed, how much reactant is consumed in the total process. So this is going to incorporate our recycle. This number we want to be very, very close to 100% for a good, economically sound design. Selectivity is important when we have multiple reactions possible. We want to know that the rate of production of our desired product is high compared to the rate of production of our undesired products. And then yield is a way of describing the process efficiency. This is the moles of reactant that react to produce your desired product compared to the moles of the limiting reactant that react. Now remember, if you have a stoichiometric feed, there isn't a limiting reactant. But when your feed is non-stoichiometric, which one will be exhausted first? That's your limiting reactant. Extent of reaction is a different way of describing this phenomenon. And extent of reaction, we use, well, I call it squiggle. If you let alpha be the stoichiometric coefficient for a component I, then beta is going to be positive alpha if it's a product, negative alpha if it's a reactant, and beta will be 0 if you have an inert present. And this allows us to do a material balance that is kind of a uniform equation. So the number of moles of species I is equal to the number of moles of species I that came into the reactor, plus this beta value times squiggle, the extent of reaction. Now, extent of reaction is a nice way to describe this because it is the same for every component, okay? It does depend on the way you wrote the reaction. So when you're comparing answers to somebody else, you may have a different number. But then if you look at your reaction, you'll see that really they are the same. And again, a quick little example here for that problem that we were doing before. If you look at the 75 moles of SO2 and 25 moles of O2 fed and do this material balance, then we find that squiggle, or the extent of reaction, is 20 for every species listed here. So this concludes this video lesson. We're going to come back and look at equilibrium in our next lesson. Thank you very much for your time.